Welcome to a captivating exploration of two of the most iconic minds in the history of physics, Albert Einstein and Isaac Newton. In this thought-provoking video, we embark on a quest to determine who deserves the title of the greatest physicist. Both Einstein and Newton have left an enduring impact on the scientific world, each pushing the boundaries of human understanding in their own remarkable way. Albert Einstein, known for his iconic equation E=mc², revolutionized physics with his groundbreaking theories of relativity. His concept of spacetime challenged conventional notions of time and space, while his work on the photoelectric effect was instrumental in the development of quantum mechanics. On the other side of the ring stands Sir Isaac Newton, whose profound contributions laid the foundation for classical physics. Newton's laws of motion and the law of universal gravitation unveiled the mechanics of the universe, allowing us to comprehend the movements of celestial bodies and objects on Earth. His mathematical prowess, exemplified through calculus, became a powerful tool for further scientific discoveries. So stick around as we delve into the physics world and compare the achievements and impact of these legends. In the end, you can help us decide who deserves the title of greatest physicist of all time. Albert Einstein, born on March 14, 1879, in Ulm, Germany, showed early signs of intellectual curiosity and creativity. As a child, he was fascinated by the mysteries of the natural world and was an avid reader, devouring books on science and mathematics. However, his formal education in school was uninspiring, leading to his teachers labeling him as a slow learner. Despite this, Einstein's passion for knowledge never waned. At the age of 16, Einstein enrolled at the Polytechnic Institute in Zurich, Switzerland, to pursue his studies in physics and mathematics. His time at the institute allowed him to delve deeper into scientific principles, particularly the works of James Clerk Maxwell on electromagnetism. This exposure ignited a lifelong fascination with the relationship between electricity, magnetism, and light. Isaac Newton, born on January 4, 1643, in Woolsthorpe, England, experienced a different upbringing from Einstein. Coming from a humble family background, Newton's early years were marked by hardship and financial struggles. Despite this, he exhibited exceptional talent in mathematics during his early education. At the age of 18, Newton joined Trinity College at the University of Cambridge, where he delved into the works of prominent mathematicians and philosophers of his time. His brilliance in mathematics quickly became evident, and he made significant advancements in the field of calculus and optics during his time at the university. The backgrounds of Einstein and Newton significantly influenced their approaches to science. Einstein's early struggles in education fostered a rebellious spirit that led him to question conventional wisdom and challenge established theories. His intellectual curiosity and desire to understand the fundamental nature of the universe paved the way for his groundbreaking theories. Newton's upbringing instilled in him a disciplined and meticulous approach to scientific inquiry. His early interests in mathematics and physics set him on a path of rigorous investigation and systematic problem-solving. Isaac Newton's contributions to physics are nothing short of revolutionary. His three laws of motion and the law of universal gravitation, formulated in his landmark work Mathematical Principles of Natural Philosophy, 1687, were groundbreaking in the realm of classical mechanics. Newton's first law, the law of inertia, states that an object at rest will remain at rest, and an object in motion will continue moving at a constant velocity unless acted upon by an external force. The second law relates force, mass, and acceleration, providing a quantitative understanding of motion. Lastly, his third law asserts that every action has an equal and opposite reaction. These laws laid the foundation for explaining the motion of objects on Earth and beyond, providing a unified framework for understanding the laws of nature. In addition to his laws of motion, Newton's work on calculus has profoundly influenced mathematics and science. He independently developed this new mathematical method to solve problems involving rates of change and integration. Calculus allowed him to derive relationships between variables in his equations and understand the motion of celestial bodies. Today, calculus is an essential tool in a wide range of scientific disciplines, from physics and engineering to economics and biology. Newton's theories on classical mechanics and natural philosophy cannot be overstated. His work provided a comprehensive description of the motion of objects and the force of gravity, setting the stage for centuries of scientific progress. Newtonian mechanics became the gold standard for explaining the behavior of macroscopic objects, and his laws became fundamental principles in the field of physics. Albert Einstein, in the early 20th century, revolutionized the field of physics with his theory of relativity. His special theory of relativity, published in 1905, introduced the concept of spacetime, where time and space are interwoven and influenced by motion. The theory presented the famous equation E=mc², demonstrating the equivalence of mass and energy, laying the groundwork for understanding the release of immense energy in nuclear reactions. Einstein's general theory of relativity, published in 1915, extended his ideas to gravity. It introduced the notion that massive objects like planets and stars curve spacetime around them, causing other objects to follow curved paths, which we perceive as gravity. This theory provided a more accurate description of the gravitational force, especially in extreme conditions, such as near black holes or during the early moments of the universe. Einstein made significant contributions to quantum mechanics, despite his initial skepticism about some aspects of the theory. He proposed the concept of the photon, a quantized particle of light, which helped explain the photoelectric effect and the dual nature of light as both waves and particles. Isaac Newton's impact on the scientific community was immense, primarily due to his seminal work, Philosophiae Naturalis Principia Mathematica, 1687. This magnum opus presented his laws of motion and the law of universal gravitation, earning him accolades and widespread recognition during his lifetime. Principia Mathematica laid the groundwork for classical mechanics, providing a comprehensive mathematical framework for understanding the motion of celestial bodies and objects on Earth. Newton's laws became fundamental principles in physics and shaped scientific thought for centuries, serving as a guiding light for subsequent generations of scientists. Albert Einstein's impact on the scientific community was equally profound, if not greater. His theories of relativity, both special and general, challenged and expanded upon Newtonian physics, revolutionizing our understanding of space, time, and gravity. Einstein's work opened up new avenues of research and led to the discovery of phenomena like time dilation, black holes, and the bending of light by gravity. Moreover, his contributions to quantum mechanics and the concept of the photon played a vital role in the development of modern physics. Einstein's theories sparked debates and controversies within the scientific community, especially concerning the nature of reality at the quantum level and the implications of his general theory of relativity. However, experimental evidence and observations over the years have consistently validated many of Einstein's predictions, solidifying his theories as cornerstones of modern physics. In comparing the impacts of Newton and Einstein on the present 21st century, it is clear that both have been indispensable to scientific and technological advancements. Newton's laws of motion and universal gravitation are still widely used in engineering, space exploration, and understanding the motion of celestial bodies. They form the basis for many technological innovations, from spacecraft trajectories to the design of bridges and buildings. On the other hand, Einstein's theories have had an even greater impact on modern science and technology. His theories of relativity are crucial for GPS systems, as they account for the time dilation effects caused by Earth's gravity and motion. Additionally, his understanding of the behavior of light and matter at the quantum level underpins much of modern quantum mechanics, which drives technological advancements in fields like computing, communication, and material science. The debate over who is the greatest physicist between Isaac Newton and Albert Einstein is a topic that has captivated the scientific community and enthusiasts alike. Both scientists have left an indelible mark on the world of physics, revolutionizing our understanding of the universe and laying the foundation for modern science. However, comparing their contributions and impact is a complex task, as they lived in vastly different eras, faced unique scientific challenges, and made groundbreaking discoveries that transformed the field of physics in distinct ways. Isaac Newton, the architect of classical mechanics, formulated his laws of motion and the law of universal gravitation in his monumental work, Philosophiae Naturalis Principia Mathematica. These laws provided a comprehensive description of the motion of objects and the force of gravity, offering a unified framework for understanding the laws of nature. Newton's ideas earned him accolades and widespread recognition during his lifetime, becoming a symbol of scientific greatness during the Enlightenment era. Albert Einstein ushered in the era of modern physics with his theories of relativity. His special theory of relativity, published in 1905, introduced the revolutionary concept of spacetime, where time and space are interwoven and influenced by motion. The theory presented the famous equation E=mc², demonstrating the equivalence of mass and energy. Einstein's general theory of relativity, published in 1915, extended his ideas to gravity, introducing the concept that massive objects curve spacetime, causing other objects to follow curved paths, which we perceive as gravity. His work went beyond classical mechanics, transforming the field of physics in the 20th century. His contributions to quantum mechanics and the concept of the photon played a crucial role in understanding the behavior of light and matter at the quantum level. Furthermore, Einstein's work had implications beyond physics, as his theory of relativity directly influenced advancements in cosmology, space exploration, and even the development of nuclear energy. In the greatest physicist debate, each scientist brings unique strengths to the table. Newton's laws govern the macroscopic world and provide a robust framework for understanding the motion of planets, stars, and objects in our daily lives. Einstein's theories dominate the realm of the very large and the very small, shaping our understanding of the cosmos on cosmic scales and the behavior of particles at the quantum level. Ultimately, determining the greatest physicist between Newton and Einstein is a subjective endeavor, heavily influenced by personal opinions and the historical context in which they lived. While Newton's contributions were revolutionary for his time, Einstein's work ushered in a new era of physics and transformed our understanding of the universe in profound ways. Perhaps, the true answer lies not in choosing one over the other, but in recognizing and celebrating the exceptional brilliance of both Isaac Newton and Albert Einstein, as they continue to inspire future generations of scientists to explore the wonders of the cosmos.